through the fire and through the flame, chasing dreams they call insane, but our eyes are just the same. Hammer strikes and echoes loud, building towers through the clouds. No one's stopping me tonight. I've got the plans, I'll win this fight. Every man builds his own way, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain. Stone by stone I carve my fate, facing trials I won't break. Every stumble fuels my flame. I'm the one who writes my name. The world's a canvas, raw and wide. I hold the brush, I won't hide. Colors bold, they light my trail. I'll succeed, I will prevail. Every man builds his own way, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain. Built his own way, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain. Every man built his own way, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain.
An introductory architecture course from the J.O.L.A.L.F would likely serve as a foundational exploration into the world of architectural design. You can anticipate learning about the fundamental principles that underpin the creation of buildings and spaces. This might involve understanding concepts like form, function, and how they interact. The course could also delve into the basic elements of architectural drawing and representation, which are essential for communicating design ideas. You might be introduced to different types of architectural projects and perhaps even touch upon the historical context that has shaped architectural styles over time. It's also plausible that the course would begin to foster an awareness of the social and environmental factors that influence architectural design decisions. Architecture worth great attention. As we double our numbers every 20 years, we must double our houses. Besides, we build of such perishable materials that one half of our houses must be rebuilt in every space of 20 years. So that in that term, houses are to be built for 3/4 of our inhabitants. It is then among the most important arts, and it is desirable to introduce taste into an art which chews so much. Thomas Jefferson, Hints to Americans Traveling in Europe, Letter to John Rutledge, Jr. June 19, 1788, in the Papers of Thomas Jefferson, ed. Julian P. Boyd 1956, Volume 13, p. 269. Architecture is the art and science of designing and constructing buildings and other physical structures. It's more than just putting up walls and a roof. It involves a thoughtful process of creating spaces that serve human needs and aspirations. Architects consider a wide range of factors, including functionality, aesthetics, safety, sustainability, and the cultural and social context of a place. They use creativity and technical knowledge to translate ideas into tangible forms, shaping the environments in which we live, work, and interact. Ultimately, architecture aims to create meaningful and enduring spaces that enhance the human experience. For instance, Geometry is fundamental. Architects constantly work with shapes, angles, volumes, and spatial relationships. They use principles of Euclidean geometry to plan layouts, define forms, and understand the properties of different geometric elements. Trigonometry comes into play when dealing with angles, slopes, and complex roof structures. Calculations involving sine, cosine, and tangent help ensure structural stability and accurate construction. Basic algebra and arithmetic are essential for calculations related to dimensions, areas, volumes, material quantities, and cost estimations. Understanding scale and proportion, which often involves ratios and fractions, is crucial for creating harmonious designs. More advanced mathematical concepts can also be relevant, depending on the specific area of architecture. For example, structural engineers, who work closely with architects, use complex equations from mechanics and materials science to ensure the stability and safety of buildings under various loads. Concepts from calculus might be used in advanced structural analysis or in optimizing building performance for energy efficiency. One structural integrity of iconic skyscrapers, the Burj Khalifa, Dubai. This record-breaking skyscraper relies heavily on advanced structural analysis. 1 Engineers used complex computer modeling and finite element analysis via a numerical technique rooted in calculus and linear algebra, to simulate wind loads, seismic activity, and the immense gravitational forces acting on the structure. 2 The Y-shaped plan was, in part, a result of optimizing the building's form mathematically to minimize wind vortex shedding, a phenomenon that can cause dangerous oscillations. 3 The tapering shape also contributes to its stability and reduces wind pressure as height increases. 4 The Sydney Opera House, Australia, the iconic sail-like roofs are a marvel of structural engineering. 5 Their complex geometry, involving hyperbolic paraboloids, required sophisticated mathematical modeling to ensure stability under various loads. Engineers used advanced calculus and matrix methods to analyze the forces acting on the thin concrete shells and design the supporting arches and ribs. Guggenheim Museum, Bilbao, Spain, Frank Gehry's fluid, titanium-clad design presented significant structural challenges. 6 The seemingly arbitrary curves and shapes were actually generated using advanced 3D modeling software that relies on complex mathematical algorithms, including non-Euclidean geometry and spline mathematics. Structural engineers then used FEA to break down these complex forms into smaller elements to analyze stress distribution and ensure the stability of the unconventional structure. 2 Optimizing building performance for energy efficiency, the Gherkin 30 St. Mary Axe, London. This distinctive building's curved shape isn't just for aesthetics, it's a result of aerodynamic studies using computational fluid dynamics (CFD), a field heavily reliant on calculus and numerical methods. The shape helps to reduce wind loads and creates pressure differentials that aid in natural ventilation, significantly reducing the building's energy consumption for cooling. Mathematical models were crucial in optimizing the building's form for these environmental benefits. Passive house design, the Passive House Standard, which aims for ultra-low energy consumption, relies heavily on mathematical modeling and simulation. 7 Architects and engineers use software that employs principles of thermodynamics and heat transfer, often expressed through differential equations, to optimize insulation, window placement, and ventilation systems. 8 These simulations predict energy performance under various climate conditions, allowing for data-driven design decisions that minimize heating and cooling needs. 9 Solar panel optimization. Architects use calculus to determine the optimal angles and placement of solar panels on building facades and roofs to maximize energy capture throughout the year. This involves understanding the changing angles of the sun and using derivatives to find the maximum power output for a given location and panel orientation. 3 Advanced geometric concepts in design. Fractal geometry in design, while not always directly involving complex equations in construction, the mathematical principles of fractal geometry inspire innovative and visually complex architectural forms. Antoni Gaudi's Sagrada Familia in Barcelona, with its branching columns and intricate details, exhibits fractal-like patterns, reflecting nature's self-similar structures. While the construction might rely on more traditional engineering calculations, the initial design concept draws from these advanced mathematical ideas. Parametric design: this approach uses algorithms and computational logic, often based on mathematical relationships, to generate and manipulate architectural forms. 10 Architects define parameters and rules, and the software explores a range of design possibilities based on these mathematical constraints. 11 This can lead to highly optimized and innovative designs that might be difficult to achieve through traditional manual methods. The process inherently involves mathematical thinking and the application of geometric principles through code. Syllabus: this course offers a foundational exploration of architectural design principles, representation, history, and context. Modules: project types and history, overview of common building types and significant architectural period styles. Design fundamentals: form, function, space, order, basic elements, line, shape, volume, light, etc. Understanding architecture vs. building. Visual communication, introduction to architectural drawings, plans, elevations, sections, basic drafting conventions, scale and proportion. Context and environment, social, cultural, and environmental influences on design, introduction to sustainability. Mathematics in architecture, basic geometry, trigonometry, angles, slopes, algebra, arithmetic, dimensions, quantities, and awareness of advanced concepts via CFD, parametric design in complex projects. Learning activities, reading introductory texts. Conducting research on architectural examples. Reflecting on design implications. Architecture may at first appear to be a more fixed and finite term. It has a three-dimensional, tangible, usable form. But questions remain about what can be considered architecture and what cannot, and by this I mean that we usually understand architecture to incorporate aesthetic as well as functional consideration into its structure. Anything that does not fall into this category can be described as just a building. This may seem too simple. Can architecture be determined solely by the use of refined architectural style, high or polite architecture instead of vernacular? Dana Arnold, Reading Architectural History 2002, ch1, Reading the Past, What is Architectural History? The origin of architecture is deeply intertwined with the earliest efforts of humankind to create shelter and define space. Long before what we recognize today as designed buildings, the fundamental need for protection from the elements and security likely spurred the first architectural acts. Initially, this would have involved utilizing readily available natural materials like branches, leaves, animal hides, and eventually stone to construct simple dwellings. These early forms of architecture were direct responses to immediate needs and the surrounding environment, demonstrating a practical understanding of materials and basic construction. Case study: J.O.L.A.L.F, Tracing the Roots of Architecture in Early Settlement. J.O.L.A.L.F, located in modern-day Turkey, provides a compelling archaeological case study that vividly illustrates the transition from simple shelters to more complex architectural forms and the integration of social and symbolic meaning in early human settlements. Inhabited from approximately 7500 BCE to 5700 BCE, this remarkably preserved site offers a window into the architectural practices and the way of life of early agricultural communities. As human societies evolved and became more settled, so too did their architectural endeavors. The transition from nomadic lifestyles to more permanent settlements around the time of the Neolithic period marked a significant turning point. This era saw the development of more stable and intentionally built structures, often incorporating rudimentary planning and organization. The emergence of agriculture and communal living likely fostered the creation of larger, shared spaces and the development of more complex building techniques. Case study: Early Jericho, from nomadic roots to planned settlement. Jericho, located near the Jordan River in the West Bank, is considered one of the oldest continuously inhabited cities in the world. Its early history provides a fascinating example of how the transition from nomadic lifestyles to settled agriculture spurred the development of more permanent and organized architectural forms. Early monumental constructions, such as the megalithic structures found in various parts of the world, suggest a growing capacity for abstract thought and social organization connected to architectural endeavors. These weren't just shelters, they often served ceremonial, ritualistic, or astronomical purposes, indicating an early integration of cultural and symbolic meaning into the built environment. The impressive scale and precise alignments of some of these prehistoric sites hint at a level of knowledge and cooperation that goes beyond simple survival. Case study: Stonehenge, monumentality, meaning, and social organization in the Neolithic. Stonehenge, located on Salisbury Plain in Wiltshire, UK, is perhaps the most iconic megalithic monument in the world. Its construction, which spans several phases from around 3000 BCE to 1600 BCE, provides a powerful case study illustrating the growing capacity for abstract thought, complex social organization, and the integration of ceremonial, ritualistic, and potentially astronomical purposes into the built environment. The subsequent rise of ancient civilizations in Mesopotamia, Egypt, and the Indus Valley witnessed an explosion of architectural innovation. These societies developed sophisticated building techniques, utilized new materials like brick and stone on a grand scale, and created distinct architectural styles that reflected their religious beliefs, social hierarchies, and technological advancements. From the ziggurats of Mesopotamia to the pyramids of Egypt and the planned cities of the Indus Valley, architecture became a powerful tool for expressing cultural identity, religious devotion, and political power, laying the groundwork for the rich and diverse architectural history that followed. Comparative case study: Ziggurats of Mesopotamia and pyramids of Egypt, monumental expressions of early civilizations. Both the ziggurats of ancient Mesopotamia and the pyramids of ancient Egypt represent significant leaps in architectural innovation, moving far beyond the simpler structures of earlier periods. They showcase the capabilities of these emerging civilizations in terms of engineering, resource management, and the translation of complex social and religious ideologies into monumental forms. The Bronze Age and Iron Age saw the rise of new empires and cultures, each leaving their unique architectural footprint. In the Mediterranean, the Minoan and Mycenaean civilizations developed sophisticated palace complexes and fortifications, showcasing advancements in construction and artistic expression. The Greeks, with their emphasis on philosophy, democracy, and humanism, developed a distinct architectural language characterized by harmonious proportions, the use of columns, Doric, Ionic, Corinthian orders, and monumental public buildings like temples, theaters, and stoas, which profoundly influenced Western architecture for centuries to come. Case study: comparing Knossos, Mycenae, and the Parthenon reveals a fascinating architectural trajectory during the Bronze and Iron Ages in the Mediterranean. Knossos showcases the sophisticated, artistic, and relatively peaceful Minoan culture. Mycenae reflects the more militaristic and power-oriented Mycenaean civilization with its fortified citadels. Finally, the Parthenon embodies the peak of classical Greek architecture, expressing their philosophical ideals, democratic values, and advancements in construction and aesthetics, leaving an enduring legacy that would shape Western architecture for millennia. These three sites illustrate the unique architectural footprints left by these influential cultures and the significant advancements made during this transformative period. The Roman Empire, building upon Greek foundations and incorporating their own engineering prowess, expanded architectural innovation on an unprecedented scale. They mastered new materials like concrete, developed sophisticated infrastructure including roads, aqueducts, bridges, and public baths, and constructed vast urban centers with monumental architecture such as forums, basilicas, triumphal arches, and amphitheaters like the Colosseum. Roman architectural principles and techniques spread throughout their vast empire, leaving a lasting legacy on urban planning and building design across Europe, North Africa, and the Middle East. Case study: the Colosseum and the Pantheon in Rome vividly illustrate the key architectural innovations of the Roman Empire. The Colosseum demonstrates their mastery of large-scale engineering and the use of concrete to create vast public spaces for entertainment. The Pantheon showcases their unparalleled ability to manipulate concrete to achieve breathtaking structural feats and create awe-inspiring interior spaces. These structures, along with the extensive infrastructure and urban planning evident throughout Rome, exemplify the Roman architectural principles and techniques that were disseminated across their empire, leaving an enduring legacy on the built environment of Europe, North Africa, and the Middle East. Rome itself serves as the ultimate case study of the transformative power of Roman architectural innovation. In other parts of the world, distinct architectural traditions continued to evolve. In Asia, ancient China saw the development of timber-framed architecture, characterized by intricate joinery and hierarchical roof structures, exemplified by imperial palaces and pagodas. The Indus Valley Civilization, despite its relatively short lifespan in the archaeological record, left behind well-planned cities with sophisticated sanitation systems and standardized brick construction, indicating a high level of urban planning and engineering. In the Americas, pre-Columbian civilizations like the Maya, Aztec, and Inca developed impressive pyramid temples, palaces, and urban centers, often intricately linked to their cosmology and utilizing locally available materials and construction techniques adapted to their diverse environments. China mastered timber frame construction with intricate joinery and hierarchical roofs like the Forbidden City. Indus Valley featured well-planned cities with grid layouts, standardized brick construction, and advanced sanitation like Mohenjo-Daro. Americas developed monumental pyramid temples and urban centers linked to their cosmology, using local materials like Teotihuacan. The period following these ancient empires saw the rise and spread of major world religions, which profoundly influenced architectural development. The construction of grand religious structures, such as Christian cathedrals in Europe, Buddhist stupas and temples in Asia, and mosques in the Middle East and beyond, became a major focus of architectural endeavor, often showcasing the most advanced engineering and artistic skills of their time and reflecting the specific theological and aesthetic principles of each faith. Different regions and cultures continued to adapt and innovate, leading to a rich tapestry of architectural styles and traditions that built upon the foundations laid by their predecessors while responding to their own unique social, cultural, environmental, and technological contexts. This ongoing evolution demonstrates architecture's dynamic nature as a reflection of human ingenuity and cultural expression across time and place. Case study: Notre Dame Cathedral, Borobudur Temple, and the Great Mosque of Isfahan, despite their distinct religious origins and architectural styles, all demonstrate the profound influence of faith on architectural development. They showcase the most advanced engineering and artistic skills of their time, used to express complex theological concepts, facilitate religious practices, and serve as powerful symbols of cultural identity and spiritual devotion. These structures stand as enduring examples of how religious beliefs have inspired human ingenuity and shaped the diverse and rich tapestry of architectural history across the globe. Brutalism, as an architectural style, emerged in the mid-20th century, gaining prominence in the 1950s through the 1970s. It is characterized by its stark, monumental appearance and a deliberate emphasis on raw, exposed construction materials, most notably concrete, often left unfinished or roughly textured. The term brutalism originates not from the word brutal in the sense of harshness, but rather from the French phrase béton brut, meaning raw concrete, which was a key material favored by early brutalist architects like Le Corbusier. Beyond the material palette, brutalist architecture often features repetitive modular elements forming imposing, geometric compositions. Buildings in this style can appear heavy and fortress-like, conveying a sense of solidity and permanence. Functionality was a primary driver of brutalist design, with the internal organization and purpose of the building often clearly expressed in its external form. There was a rejection of ornamentation and a focus on the honest expression of structure and materials. Brutalism gained traction in post-war Europe as a means of quickly and affordably constructing large-scale housing, educational facilities, and government buildings. It was seen by some as a progressive and socially conscious approach to architecture, reflecting a desire for honesty and utility in building design. However, the style also faced criticism for its perceived coldness, lack of human scale, and susceptibility to weathering and staining, which could detract from its intended aesthetic over time. Despite its controversial nature, brutalism remains a significant and influential architectural movement, with notable examples found across the globe, and it continues to be re-evaluated and appreciated for its bold and uncompromising aesthetic. Case study: the Unité habitation in Marseille, France, designed by Le Corbusier and completed in 1952, is frequently cited as a seminal case study of brutalist architecture. 1 This massive, multi-family housing block embodies many key characteristics of the style. 2 Its exposed, rough-cast concrete surfaces béton brut are immediately apparent, showcasing the raw materiality that defines brutalism. The building's modular design, with repetitive prefabricated apartment units stacked vertically, expresses a functionalist approach to housing. 3 The bold, unadorned facade, punctuated by deeply recessed balconies, creates a strong, monumental presence. Furthermore, the Unité habitation integrated communal facilities like a roof terrace, shops, and a kindergarten, reflecting a social vision that was often associated with early brutalist ideals of creating self-contained urban communities. This project powerfully demonstrates the core tenets of brutalism: raw materials, functional expression, monumental scale, and a rejection of traditional ornamentation. Design Fundamentals delves into the very essence of what constitutes architectural creation, moving beyond the mere assembly of materials to fulfill a basic need for shelter. It begins with the exploration of form, which refers to the three-dimensional shape and structure of a building or space. Form is not arbitrary, it is often influenced by function, materials, structural requirements, and aesthetic considerations. The interplay of positive forms the building itself and negative forms the spaces around and within it is crucial in shaping the user experience. Closely intertwined with form is function, which addresses the intended purpose and use of a building or space. A well-designed piece of architecture seamlessly accommodates its intended activities, ensuring efficiency, comfort, and usability. The relationship between form and function is often a central tenet of architectural design, with successful architecture achieving a harmonious balance between the two. Case study: the Bauhaus Dessau building, designed by Walter Gropius, stands as a powerful case study in the fundamental design relationship between form and function, where the building's aesthetic is directly derived from the clear expression of its various uses. The distinct forms of the glazed workshop wing, the studio dormitory block with individual balconies, the connecting bridge housing offices and dining, and the more enclosed auditorium and cafeteria all articulate their specific functions. This intentional design, rejecting ornamentation in favor of functional clarity, extends to the interplay of positive building forms and the negative spaces they define, both externally and internally. The success of the Bauhaus Dessau lies in its harmonious balance of form and function, making it an iconic example of modernist architecture and the principle that form should rigorously follow function to create efficient and aesthetically significant spaces. The concept of space in architecture goes beyond mere emptiness. It refers to the intentionally shaped and organized volumes that define and are defined by architectural forms. Architects manipulate spatial relationships to create different experiences, from intimate and enclosed spaces to expansive and open ones. The flow of space, the connection between interior and exterior spaces, and the hierarchy of spaces within a building are all critical aspects of architectural design. Order in architecture refers to the underlying principles and systems that bring coherence and unity to a design. This can manifest in various ways, such as symmetry, rhythm, hierarchy, datum lines, and grids. Order provides a sense of logic, clarity, and visual harmony, making a building or space feel intentional and comprehensible. Case study: the Salk Institute, designed by Louis Kahn, masterfully demonstrates the intentional manipulation of space and the application of order to create an environment conducive to scientific research and contemplation. The dramatic central court, a vast travertine plaza bisected by a channel of water flowing towards the ocean, serves as a powerful void fostering serenity and intellectual focus, while the laboratory blocks offer carefully defined volumes maximizing natural light. Kahn's design employs a strong sense of symmetry and axiality, with mirroring laboratory blocks creating balance and monumentality, and a clear hierarchy of served and servant spaces enhancing functionality. The deliberate connection between interior research areas and the exterior environment further contributes to the Institute's profound sense of place and purpose, showcasing how the thoughtful orchestration of space and order can profoundly impact human experience within architecture. Framing in architecture refers to the structural skeleton of a building, the system of interconnected elements that provide support and shape. It's the fundamental framework that carries the weight of the building and resists various loads, such as gravity, wind, and seismic forces, transferring them safely to the foundation. Framing essentially defines the building's form and provides the necessary structure for attaching walls, floors, roofs, and finishes. The choice of framing system significantly influences the building's design, cost, construction methods, and overall performance. Common framing materials include wood, engineered wood products, and structural steel, each with its own characteristics, advantages, and applications depending on the building type, scale, and local building codes. Different framing techniques, such as platform framing, balloon framing, post and beam, and steel framing, have evolved to suit various construction needs and material properties. Case study: the Crystal Palace designed by Joseph Paxton for the Great Exhibition of 1851 in London serves as an early and remarkable case study in the innovative use of a modular framing system. Paxton, a gardener and greenhouse designer, conceived of a vast structure primarily constructed of prefabricated iron components and glass panels. This modular approach allowed for rapid assembly on site, a crucial factor given the tight time frame for the exhibition. The framing system consisted of a grid of cast iron columns and wrought iron beams, repeated and interconnected to create a massive, light-filled hall. The standardization of these framing elements not only sped up construction but also allowed for efficient material use and potential disassembly and reuse, showcasing an early understanding of modularity and resourcefulness in architectural framing. The Crystal Palace demonstrated the potential of a systematic and prefabricated framing approach to create large-scale and innovative architectural spaces. Underpinning these broader concepts are the basic elements of design, which serve as the fundamental vocabulary of architecture. Line can define edges, create movement, and articulate form. Shape, a two-dimensional outline, contributes to the visual character of a building or its components. Volume describes the three-dimensional mass of a building or the spaces within it. Light, both natural and artificial, plays a crucial role in shaping perception, defining form, creating atmosphere, and influencing the usability of spaces. Color evokes emotions, defines areas, and contributes to the aesthetic identity of a building. Texture, the surface quality of materials, adds tactile and visual interest. These basic elements are the building blocks that architects manipulate to create meaningful and impactful designs. Finally, the understanding of architecture versus building is a fundamental distinction. While a building may simply serve a functional purpose as shelter, architecture transcends this basic need through thoughtful design that considers aesthetics, human experience, cultural context, and enduring quality. Architecture involves a deliberate artistic and intellectual process that aims to create spaces that are not only functional but also meaningful and enriching. Case study: the Barcelona Pavilion, designed by Ludwig Mies van der Rohe for the 1929 International Exposition, serves as a concise case study demonstrating the powerful manipulation of basic design elements to transcend mere building and achieve impactful architecture. The pavilion's elegant simplicity showcases how carefully considered lines define planes and volumes, while the interplay of rectangular shapes creates a dynamic spatial flow. The strategic use of natural light, filtered through translucent and transparent surfaces, sculpts the interior and emphasizes the rich textures of marble, glass, and steel. Color is subtly employed through the inherent hues of the materials, contributing to the pavilion's refined aesthetic. Ultimately, the Barcelona Pavilion, devoid of overt ornamentation, exemplifies how the deliberate and masterful application of fundamental design elements elevates a functional structure into a profound architectural experience that continues to influence design thinking about space, form, and material expression. Visual communication forms the essential language through which architectural ideas are conceived, developed, and conveyed to others, including clients, engineers, contractors, and the public. The foundation of this communication lies in architectural drawings, which are standardized graphical representations of buildings and spaces. Plans are horizontal sections showing the layout of spaces and their relationships from a viewpoint above. Elevations are orthographic projections showing the exterior vertical faces of a building. Sections are vertical cuts through a building, revealing the interior organization and the relationship between different levels. These drawings provide critical information about the size, shape, and spatial arrangement of a design. Case study: the design and construction documentation for the Sydney Opera House, while complex, serves as a powerful case study in the necessity and efficacy of visual communication in architecture. Jorn Utzon's initial conceptual sketches, though evocative, required translation into precise architectural drawings, including detailed plans illustrating the layout of the various performance spaces and public areas, intricate elevations capturing the iconic sail-like roof structures from multiple viewpoints, and numerous sections revealing the internal construction and acoustic design. These standardized graphical representations, adhering to drafting conventions and utilizing scale and proportion accurately, were crucial for conveying the innovative and challenging design to engineers, contractors, and ultimately for the successful realization of this globally recognized architectural masterpiece, demonstrating how clear and comprehensive visual communication bridges the gap between concept and built reality. To ensure clarity and accuracy, architects adhere to basic drafting conventions. These include standardized line weights to indicate different elements, e.g. walls, windows, dimensions, symbols for materials and fixtures, and annotations providing crucial information. Consistency in these conventions allows for universal understanding across the construction industry. Scale is a fundamental concept in architectural drawing, representing the proportional relationship between the drawing and the actual building. Drawings are typically created at a reduced scale, e.g. 150, 1:100 to fit on manageable paper sizes while still conveying accurate dimensions. Understanding and interpreting scale is crucial for comprehending the true size and proportions of a design. Proportion, on the other hand, refers to the harmonious relationship between different parts of a building or space. Architects carefully consider proportions to create visually pleasing and balanced designs, often drawing upon historical precedents and mathematical principles to achieve aesthetic harmony. Mastering visual communication through these drawings and conventions is a cornerstone of architectural practice, enabling the translation of abstract ideas into tangible build form. Case study: the standardized set of architectural drawings for the Seagram building in New York City, designed by Ludwig Mies van der Rohe and Philip Johnson, exemplifies the critical role of basic drafting conventions, scale, and proportion in ensuring clarity and accuracy throughout the design and construction process. The consistent use of precise line weights to differentiate structural elements from glazing and dimensions, standardized symbols for materials like steel and glass, and meticulous annotations detailing specifications allowed for universal understanding among the diverse team involved. The drawings, rendered at appropriate scales, accurately conveyed the building's monumental yet refined proportions, reflecting Mies's philosophy of less is more and achieving a timeless aesthetic harmony through carefully considered ratios and relationships between its structural grid, glass curtain wall, and bronze details, ultimately translating a sophisticated abstract concept into a tangible and influential build form. Context and environment underscores the critical understanding that architecture does not exist in a vacuum but is deeply intertwined with its surroundings and the human activities it shelters. Social influences on design encompass the needs, values, behaviors, and cultural practices of the people who will inhabit and interact with a building or space. Architects must consider demographics, social structures, community needs, and accessibility to create designs that are inclusive, functional, and responsive to the social fabric. Cultural influences are equally significant, shaping architectural styles, material choices, and symbolic meanings. Historical traditions, local customs, religious beliefs, and aesthetic preferences all contribute to the unique character of architecture in different regions and societies. Understanding and respecting these cultural nuances is essential for creating contextually appropriate and meaningful designs. Case study: the traditional courtyard houses of Beijing, known as Saihewan, serve as a compelling case study illustrating the profound influence of context and environment on architecture. These dwellings are deeply rooted in Chinese social structures, where the enclosed courtyard provided privacy and security for extended families living together, reflecting Confucian values of hierarchy and familial harmony. Culturally, the orientation of the houses, the layout of rooms, and the placement of elements like the main gate and ancestral shrine were dictated by Feng Shui principles and long-standing traditions. Environmentally, the inward-facing design offered protection from the harsh Beijing climate, creating a microclimate within the courtyard that provided shade in summer and shelter in winter, while the use of locally sourced materials like brick and timber further integrated the architecture with its surroundings, demonstrating a harmonious response to both social needs and cultural beliefs within a specific environmental context. Furthermore, environmental influences on design are increasingly paramount in contemporary architectural practice. Climate, topography, site conditions, and the availability of local resources all play a crucial role in shaping building form and material selection. Architects must consider factors such as solar orientation, wind patterns, natural light, and rainwater harvesting to create buildings that are responsive to their environment and minimize their ecological impact. This leads directly to the introduction to sustainability in architecture. Sustainable design aims to create buildings and environments that meet the needs of the present without compromising the ability of future generations to meet their own needs. This involves considering the entire life cycle of a building, from material sourcing and construction to operation, maintenance, and eventual demolition. Principles of sustainability include energy efficiency, water conservation, the use of renewable resources, minimizing waste, and creating healthy indoor environments. Integrating social, cultural, and environmental considerations into the design process is no longer an option but a necessity for creating responsible and resilient architecture that contributes positively to both human well-being and the planet. Case study: the Bullitt Center in Seattle, Washington, stands as a compelling case study in contemporary architecture that deeply integrates environmental influences and sustainability principles. Designed to meet the rigorous living building challenge, the Bullitt Center meticulously considers its climate through passive design strategies like maximizing daylight and natural ventilation, utilizes the site's geothermal energy for heating and cooling, harvests rainwater for all water needs, and incorporates composting toilets to manage waste on site. Its form and material choices were driven by minimizing environmental impact and maximizing resource efficiency, aiming for net zero energy and water consumption while creating a healthy and inspiring indoor environment. This holistic approach, considering the entire life cycle of the building and its interaction with the local ecology, demonstrates a profound commitment to creating responsible and resilient architecture that serves both human well-being and the planet. Mathematics in architecture provides the fundamental quantitative framework that underpins the translation of design concepts into buildable realities. Basic geometry is indispensable, as architects constantly work with shapes, angles, volumes, and spatial relationships. Understanding Euclidean geometry is essential for planning layouts, defining forms, calculating areas and volumes, and ensuring the accurate representation of designs in drawings. Trigonometry becomes crucial when dealing with angles, slopes, and complex roof structures. Calculations involving sine, cosine, and tangent are necessary for ensuring structural stability, accurate construction of angled elements, and determining solar angles for energy efficiency. Case study: a unique case study illustrating the fundamental role of basic geometry and trigonometry in architecture is the design and construction of geodesic domes, popularized by Buckminster Fuller. These spherical or partial spherical structures are based on geodesic polyhedra, which are polyhedra composed of triangular facets approximating a sphere. The inherent strength and efficiency of a geodesic dome arise directly from its geometric configuration. The division of the sphere into interconnected triangles creates a lightweight yet incredibly strong structure that can span large distances without internal supports. The precise angles and lengths of the struts forming the triangular facets are determined through complex geometric calculations and trigonometric relationships. Fuller's innovative approach utilized mathematical principles to create a structural system that maximized volume while minimizing surface area and material use. The unique curvature of the dome and the interconnected triangular network distribute stress evenly across the structure, a principle understood and applied through geometric and trigonometric analysis. The successful construction of numerous geodesic domes for diverse applications, from exhibition halls to housing, stands as a testament to the power of applying fundamental mathematical concepts to create innovative and structurally sound architectural forms. Basic algebra and arithmetic are fundamental for a wide range of architectural calculations, including determining dimensions, areas, volumes of materials, and cost estimations. Understanding ratios and proportions is essential for working with scale in drawings and for creating aesthetically pleasing and well-proportioned designs. Beyond these basics, an awareness of advanced concepts in mathematics becomes relevant for specific aspects of architectural practice. Finite element analysis (FEA), rooted in calculus and linear algebra, is a powerful computational tool used by structural engineers who work closely with architects to analyze the structural integrity of complex buildings under various loads, such as wind and seismic forces. Computational fluid dynamics (CFD), relying heavily on calculus and numerical methods, is used to simulate airflow, heat transfer, and other fluid phenomena to optimize building performance for energy efficiency and occupant comfort. Parametric design, an increasingly prevalent approach, utilizes algorithms and computational logic based on mathematical relationships to generate and manipulate architectural forms. Architects define parameters and rules, and software explores a range of design possibilities based on these mathematical constraints, leading to highly optimized and innovative designs. While not every architect needs to be a mathematician, a solid understanding of basic mathematical principles and an awareness of how advanced mathematical tools can be applied are essential for creating safe, efficient, and innovative architectural solutions. Case study: a compelling case study illustrating the fundamental role of basic algebra and arithmetic, alongside the application of advanced mathematical concepts, is the design and construction of the Millau Viaduct in France, designed by Michel Verlaguer and Norman Foster. The initial design and cost estimations for this record-breaking cable-stayed bridge relied heavily on basic algebra and arithmetic to calculate dimensions, material quantities, steel, concrete, and projected costs. Understanding ratios and proportions was crucial in determining the elegant slenderness of the piers and the span lengths, contributing to the bridge's aesthetic appeal while adhering to structural requirements. However, the realization of such a complex structure demanded the application of advanced mathematical concepts. Finite element analysis (FEA) was extensively used by structural engineers to model and analyze the immense forces acting on the bridge, including wind loads across the valley and the tension in the cables supporting the deck. CFD simulations were likely employed to understand and mitigate the aerodynamic forces acting on the tall piers and the deck in the wind. Furthermore, the precise curvature of the deck and the optimized geometry of the cable stays likely involved parametric design principles, where algorithms based on mathematical relationships were used to generate and refine the form for both structural efficiency and aesthetic harmony. The Millau Viaduct stands as a testament to how a solid foundation in basic mathematical principles, coupled with the strategic application of advanced analytical and generative tools, enables the creation of groundbreaking and structurally sound architectural and engineering marvels. AutoCAD architecture is a specialized version of the widely used AutoCAD software, specifically tailored to the needs and workflows of architects. It goes beyond the general drafting capabilities of standard AutoCAD by offering intelligent building design tools and features that streamline the architectural design and documentation process. Instead of just lines, arcs, and circles, AutoCAD architecture enables users to work with parametric architectural objects like walls, doors, windows, stairs, and roofs. These objects behave intelligently, meaning they understand their real-world counterparts and can interact with each other in a meaningful way. For instance, when a door is inserted into a wall, the software automatically creates an opening of the correct size. Similarly, modifying a wall can automatically update any connected objects. This object-based approach significantly enhances efficiency and reduces the time spent on repetitive tasks. Architects can quickly create and modify building layouts, knowing that the software is managing many of the underlying geometric relationships and data. AutoCAD architecture also provides extensive libraries of architectural symbols and details, further accelerating the drafting process and ensuring adherence to industry standards. Beyond basic drawing, AutoCAD architecture offers features for creating and managing building information. It allows users to generate schedules for doors, windows, and finishes directly from the model, ensuring accuracy and consistency in documentation. The software also facilitates the creation of elevations, sections, and 3D visualizations, enabling a comprehensive understanding of the design from different perspectives. While it might not be a full building information modeling BIM software like Revit, AutoCAD architecture incorporates some BIM-like capabilities, allowing for a more data-rich and coordinated design process compared to traditional 2D drafting. Furthermore, AutoCAD architecture provides tools for annotating drawings with dimensions, notes, and tags that are linked to the architectural objects. This dynamic linking ensures that when the design changes, the annotations update automatically, reducing errors and saving time during revisions. The software also supports collaboration through features like ECRIF's external references, allowing multiple team members to work on different parts of a project simultaneously while maintaining a coordinated overall drawing set. In essence, AutoCAD architecture serves as a powerful and efficient drafting and documentation tool specifically designed to enhance the productivity and accuracy of architects in bringing their designs to life in a digital environment. Case study: a compelling case study illustrating the benefits of using AutoCAD architecture is the design and documentation of a medium-sized residential housing project, such as a complex of townhouses or a multi-unit dwelling. Imagine a small architectural firm tasked with designing a development of 10 two-story townhouses, each with a slightly different layout but sharing common wall types, window sizes, and roof pitches. Using standard AutoCAD would involve drawing each line and object individually for every unit, manually creating door and window schedules, and painstakingly updating drawings whenever a change occurred. This would be a time-consuming and error-prone process. However, by utilizing AutoCAD architecture, the firm can significantly streamline this workflow. They can define parametric wall styles with specific thicknesses and material properties. Point 1. Inserting a standard window or door object automatically creates the correct opening in any wall type used. If a client requests a change to the window size across all units, the architect can modify the window style once, and all instances in the plans, elevations, sections, and schedules update dynamically. The software's ability to generate automatic door and window schedules directly from the placed objects eliminates the need for manual data entry and reduces the risk of discrepancies between drawings and schedules. Creating elevations and sections becomes more efficient as the software understands the 3D relationships between the architectural objects, allowing for quicker generation of these views. Furthermore, if the overall site plan requires adjustments to the layout of the townhouses, moving a unit will automatically update its position in all relevant drawings. The use of ECRIFs allows different team members to work on individual townhouse units or specific drawing set site plan, floor plans, elevations concurrently, improving collaboration and reducing overall project timelines. Point 2. Annotations, such as dimensions and tags, linked to the architectural objects ensure that any design revisions are automatically reflected in the documentation, maintaining accuracy and reducing the potential for costly errors during construction. In this scenario, AutoCAD architecture's intelligent objects, automated scheduling, and coordinated drawing views would lead to a significantly faster and more accurate design and documentation process compared to standard AutoCAD. Point 3. The time saved on repetitive tasks allows the architects to focus more on design quality and client communication, ultimately leading to a more efficient and successful project delivery. Point 4. Architectural surveying is a specialized field that focuses on the precise measurement, documentation, and analysis of existing buildings, structures, and sites. Unlike general land surveying, which often deals with broader topographical features and property boundaries, architectural surveying delves into the intricate details of the built environment. It's a critical process that provides architects, designers, and other professionals with the accurate information needed for a variety of purposes, including renovation, restoration, adaptive reuse, extensions, and the creation of as-built drawings. The process typically involves a meticulous on-site investigation using a range of tools and techniques. Traditional methods like tape measures, levels, and plumb bobs are still employed for certain aspects, especially for detailed internal measurements. However, modern architectural surveying increasingly relies on advanced technologies to capture data efficiently and accurately. Total stations, which combine electronic distance measurement (EDM) with angle measurement capabilities, allow surveyors to record thousands of precise points, creating a detailed three-dimensional representation of the building or site. Laser scanners are another powerful tool, capable of capturing millions of data points rapidly, resulting in a dense point cloud that can be used to generate highly accurate 3D models. Drones equipped with photogrammetry or LiDAR light detection and ranging technology are also becoming increasingly common for surveying larger or more complex sites and building exteriors, providing aerial perspectives and detailed surface information. The data collected during an architectural survey is then processed and translated into various deliverables. These typically include detailed floor plans, elevations showing the vertical facades, sections revealing the internal organization, and often 3D models that provide a comprehensive spatial understanding of the existing conditions. The level of detail and accuracy required depends on the specific project needs. For instance, a survey for a minor interior renovation might not require the same level of precision as a survey for the restoration of a historic facade. Beyond geometric data, architectural surveys can also document other crucial aspects of a building, such as the materials used, structural elements, existing services, electrical, plumbing, HVAC, and any signs of deterioration or structural issues. This comprehensive information allows architects to make informed design decisions, identify potential challenges early in the project, and create accurate and buildable designs that respond effectively to the existing context. Ultimately, architectural surveying provides the essential foundation of accurate information upon which successful architectural projects involving existing structures are built. Case study: a compelling case study illustrating the critical role of architectural surveying is the restoration of a significant historic building, such as the Melbourne Town Hall in Melbourne, Australia. Point 1. Over its long history, the Melbourne Town Hall has undergone various modifications and experienced the wear and tear of time. Before any major restoration or renovation work can be undertaken, a comprehensive architectural survey is absolutely essential to accurately understand the existing fabric of the building. Point 2. Initially, surveyors would employ traditional methods to meticulously measure and document the grand spaces, intricate plasterwork, ornate facades, and existing structural elements. They would record the precise dimensions of rooms, the height of ceilings, the location and size of windows and doors, and the details of architectural features. Point 3. However, for a building of this scale and historical significance, modern technologies would also be crucial. Laser scanners would be deployed to capture highly accurate three-dimensional point clouds of both the interior and exterior. This data would provide an incredibly detailed digital representation of the building's current state, capturing even subtle irregularities and deformations that might not be apparent with traditional methods. Drones equipped with photogrammetry could be used to create detailed aerial views and 3D models of the roof and upper facades, areas that are difficult and costly to access manually. The resulting data would then be processed to generate a comprehensive set of architectural drawings, including highly accurate floor plans, detailed elevations of each facade, and precise sections revealing the internal construction and spatial relationships. Crucially, the survey would also document the existing materials used throughout the building, noting their condition and any signs of deterioration, such as cracking in the stonework or damage to the plasterwork. Point 4. The location and type of existing services. Electrical wiring, plumbing, historical heating systems would also be meticulously recorded. This detailed architectural survey would provide the architects and restoration specialists with an invaluable baseline understanding of the Melbourne Town Hall. It would allow them to accurately plan the restoration work. Knowing the precise dimensions and condition of existing elements is crucial for designing appropriate repairs and replacements. Identify structural issues. The survey data can reveal any structural weaknesses or areas requiring reinforcement. Point 5. Recreate historical details. Accurate measurements and 3D models facilitate the faithful replication of original architectural features. Point 6. Integrate new services sensitively. Understanding the location of existing services helps in planning the installation of modern amenities without damaging the historical fabric. Create accurate as-built drawings. The survey forms the basis for updated documentation of the building in its current state, essential for future maintenance and modifications. Point 7. Process architecture, in the context of enterprise or business architecture, focuses on defining and understanding the sequence of activities, workflows, and interactions within an organization that deliver value. It's about mapping out how work gets done, rather than the physical structures or software applications that support it. Process architecture aims to provide a clear and comprehensive view of an organization's core operational activities, their dependencies, the information and resources they utilize, and the outcomes they produce. A well-defined process architecture helps to identify bottlenecks, inefficiencies, redundancies, and areas for improvement within an organization. It serves as a blueprint for business process re-engineering, automation initiatives, and the alignment of IT systems with business goals. By visualizing the flow of work, stakeholders can gain a shared understanding of how the organization functions, facilitating better communication and decision-making. Process architecture typically involves identifying and documenting different levels of processes, from high-level value streams down to detailed task descriptions. Various modeling techniques, such as BPM and business process model and notation, flowcharts, and value stream maps, are used to visually represent these processes. The architecture also considers the roles and responsibilities of individuals and teams involved in each process, as well as the systems, data, and policies that govern them. Ultimately, process architecture provides a framework for analyzing, designing, and optimizing the way an organization operates to achieve its strategic objectives. Case study. A compelling case study illustrating the value of process architecture is the re-engineering of the order fulfillment process at a large e-commerce retailer facing significant challenges with delivery times, customer satisfaction, and operational costs. Initially, the retailer's order fulfillment process had evolved organically over time, resulting in a complex web of disconnected steps involving multiple departments, manual data entry, and a lack of clear accountability. Customer orders would meander through various systems, leading to delays, errors in shipping, and difficulty in tracking order status, ultimately impacting customer satisfaction and increasing operational expenses due to rework and expedited shipping. To address these issues, the retailer embarked on a process architecture initiative. They began by mapping the as-is state of their order fulfillment process, documenting every step from when a customer placed an order online to when the product was delivered. This involved interviewing stakeholders from different departments: sales, warehousing, packing, shipping, customer service, analyzing existing systems and data flows, and visually representing the process using BPMN diagrams. The as-is process map revealed numerous inefficiencies, redundant data entry points, manual handoffs between departments causing delays, a lack of real-time inventory visibility leading to back orders, and a fragmented system landscape where information wasn't easily shared. Bottlenecks were identified in the warehouse picking and packing stages, and the lack of automated tracking made it difficult for customer service to provide accurate updates. Based on this analysis, the retailer developed a to-be process architecture. This involved redesigning the order fulfillment process with a focus on streamlining workflows, automating manual tasks, and improving information flow. Key changes included implementing an integrated order management system. This centralized order data, providing real-time visibility to all relevant departments. 1. Automating warehouse processes, introducing barcode scanning for inventory management and order picking, and optimizing warehouse layout for efficient movement. Streamlining the packing and shipping stages, implementing automated label generation and integrating with shipping carriers for real-time tracking updates. 2. Establishing clear roles and responsibilities, defining ownership for each step in the process and implementing performance metrics. The to-be process architecture was again documented using BPMN diagrams, clearly outlining the new sequence of activities, system interactions, and data flows. This served as a blueprint for the implementation of new technologies and the retraining of staff. The results of this process re-engineering initiative, guided by the process architecture, were significant. Delivery times were reduced by 30%, customer satisfaction scores improved by 20%, and operational costs associated with order fulfillment decreased by 15% due to reduced errors and increased efficiency. The clear visualization of the process also facilitated better communication and collaboration between departments, fostering a more customer-centric approach. This case study demonstrates how a well-defined process architecture can provide a critical understanding of an organization's operations, identify areas for improvement, and serve as a roadmap for successful business transformation, leading to tangible benefits in terms of efficiency, customer satisfaction, and cost reduction. Naval architecture is the engineering discipline that encompasses the design, construction, maintenance, and operation of marine vessels and structures. Unlike traditional architecture focused on land-based buildings, naval architecture deals with the unique challenges and physical principles associated with operating in a fluid environment. It's a multidisciplinary field that integrates aspects of mechanical, electrical, electronic, software, and safety engineering, all applied to the specific context of ships, boats, submarines, offshore platforms, and other floating or submerged structures. At its core, naval architecture involves balancing a complex interplay of factors. Hydrostatics, the study of fluids at rest, is crucial for determining buoyancy, stability, trim, the longitudinal angle of the vessel, and the vessel's ability to float safely. Hydrodynamics, the study of fluids in motion, addresses how water flows around the hull, influencing resistance, propulsion efficiency, and maneuverability. Structural integrity is paramount, requiring naval architects to select appropriate materials and design robust frameworks capable of withstanding the various loads encountered at sea, from hydrostatic pressure to the dynamic forces of waves and storms. The design process in naval architecture is iterative and involves a deep understanding of the vessel's intended mission. Whether it's a cargo ship designed for maximum carrying capacity, a high-speed ferry prioritizing passenger comfort and speed, or a naval warship engineered for combat effectiveness, the requirements dictate the design priorities. Naval architects must consider factors like payload capacity, speed requirements, range, stability in various sea states, safety regulations, and cost effectiveness. This often involves making complex compromises and utilizing advanced engineering tools and computational methods to predict the vessel's performance even before it's built. The history of naval architecture has evolved from empirical craftsmanship to a more rigorous scientific discipline, particularly with advancements during the Industrial Revolution. Today, it relies heavily on computer-aided design CAD software, computational fluid dynamics CFD for hull optimization, and finite element analysis FEA for structural analysis. Despite these technological advancements, the art of naval architecture still involves a degree of intuitive understanding and the ability to integrate diverse engineering principles to create safe, efficient, and seaworthy vessels that serve a multitude of purposes on our water-covered planet. Case study: a compelling case study that integrates mathematical applications, sustainability considerations, and the critical distinction between architecture and building is the design and ongoing evolution of the Earthship biotecture concept, pioneered by architect Michael Reynolds. 1. Case study: Earthship biotecture, integrating math, sustainability, and the essence of architecture. Earthships are autonomous, off-the-grid dwellings constructed from natural and recycled materials like tires, earth-filled walls, and glass bottles. 2. Their design philosophy fundamentally intertwines mathematical principles with a deep commitment to environmental sustainability, pushing the boundaries of what constitutes not just a building, but a truly self-sufficient and contextually responsive piece of architecture. Mathematical applications in Earthship design. The design of Earthships necessitates numerous mathematical calculations. Determining the optimal angle for the south-facing window wall to maximize passive solar gain throughout the year requires trigonometric calculations based on the local latitude. 3. Calculating the thermal mass provided by the earth-filled tires and walls involves understanding volume, density, and heat transfer coefficients. Designing the rainwater harvesting and storage systems demands precise calculations of roof area, average rainfall, and water usage to ensure self-sufficiency. 4. Even the structural stability of the tire walls and the roof systems relies on basic geometric principles and load calculations. 5. These mathematical considerations are not merely applied after a design is conceived, they are integral to shaping the very form and orientation of an Earthship. Deep integration of sustainability. Sustainability is not an add-on but the core principle driving Earthship design. 6. The use of recycled materials minimizes waste and embodies a circular economy approach. 7. Passive solar heating and cooling, achieved through orientation, thermal mass, and ventilation strategies, drastically reduce or eliminate the need for conventional HVAC systems. 8. Rainwater harvesting and on-site water treatment promote water independence. 9. Integrated food production through interior greenhouses further enhances self-sufficiency and reduces reliance on external resources. 10. The entire design ethos prioritizes living in harmony with the local environment, minimizing ecological footprint, and creating resilient, self-sustaining habitats. Elevating building to architecture. Earthships transcend the notion of mere building through their profound engagement with their context and their aim to enhance the lives of their inhabitants in a holistic way. 11. They are not simply shelters but rather carefully calibrated ecosystems designed to provide comfort, sustenance, and a deep connection to natural cycles. The aesthetic, often characterized by organic forms and the exposed textures of the recycled materials, is a direct result of the functional and sustainable principles guiding the design. Reynolds's work goes beyond just creating habitable structures, It proposes a radical rethinking of how we live and interact with our environment. Point 12 Earthships embody an architectural philosophy that prioritizes autonomy, environmental responsibility, and a symbiotic relationship between humans and nature. Point 13 The ongoing experimentation and adaptation of Earthship designs in diverse climates and cultural contexts demonstrate a continuous striving for a truly responsive and meaningful architecture that addresses fundamental human needs while respecting planetary boundaries. In conclusion, the Earthship biotecture concept serves as a powerful case study demonstrating the inseparable link between mathematical understanding, a deep commitment to sustainability, and the creation of architecture that goes beyond basic shelter to offer a holistic and environmentally conscious way of living. The mathematical calculations are not just tools for construction but drivers of form and efficiency, while sustainability is the core ethos that elevates these structures to a form of architecture that actively engages with and respects its context. Architecture code, at its heart, embodies the fundamental principles, patterns, and practices that guide the design, development, and evolution of a software system. It's the blueprint that shapes the structure, behavior, and qualities of the software. Think of it as the underlying skeleton and organizational framework. It defines the major components, their responsibilities, and how they interact with each other. This includes decisions about the overall system structure, such as whether to use a monolithic, microservices, or event-driven architecture. Architecture code also encompasses the selection of technologies, frameworks, and tools that will be used to build the system. These choices have significant implications for performance, scalability, maintainability, and security. Furthermore, it establishes the non-functional requirements, often referred to as the UTILities, such as reliability, usability, performance, scalability, maintainability, and security. These qualities are not about what the software does, but rather how well it does it. The architecture code sets the stage for achieving these critical attributes. Beyond the technical aspects, architecture code often reflects the business context and constraints. It considers factors like budget, timelines, team skills, and the long-term vision for the product. In essence, architecture code is the intellectual scaffolding that ensures the software is not just a collection of working parts, but a cohesive, robust, and adaptable solution that meets both current and future needs. It provides a shared understanding among the development team and stakeholders, facilitating communication and collaboration throughout the software lifecycle. Case study: consider the collapse of the Rana Plaza garment factory in Bangladesh in 2013. This tragic event, which resulted in the deaths of over 1,100 people, serves as a stark and compelling case study highlighting the catastrophic consequences of inadequate building codes and their enforcement. The Rana Plaza was an illegally constructed, multi-story commercial building that housed several garment factories. Despite visible structural weaknesses and warnings, factory owners pressured workers to continue operations. The eventual collapse exposed widespread violations of existing building codes and a complete lack of effective oversight. Architecture law, at its core, is the body of legal principles and regulations that govern the practice of architecture and the design and construction of buildings. It establishes the rights, responsibilities, and liabilities of architects, clients, contractors, and other stakeholders involved in the built environment. This legal framework defines the professional standards architects must adhere to, including licensing requirements, ethical obligations, and the scope of their services. Architecture law also encompasses the contractual agreements between parties, outlining the terms of engagement, payment schedules, and intellectual property rights related to architectural designs. Furthermore, it interacts closely with building codes and zoning regulations, ensuring that architectural designs comply with safety standards, land use restrictions, and environmental considerations. Ultimately, architecture law aims to create a framework that promotes responsible and competent architectural practice, protects the interests of all involved parties, and contributes to the creation of a safe, functional, and aesthetically pleasing built environment. Case study: consider the ongoing legal debates surrounding starchitect designs and their impact on local urban contexts and heritage preservation. This presents a compelling case study in architecture law, specifically concerning the balance between innovative design and the preservation of established urban fabric and historical significance. In many cities around the world, iconic, often large-scale buildings designed by internationally renowned architects starchitects have sparked significant legal challenges and public discourse. These projects can clash with existing zoning regulations, heritage protection laws, and local community aesthetics. Here's how this scenario highlights key aspects of architecture law, zoning and land use regulations. Starchitect designs often push the boundaries of existing zoning laws regarding height restrictions, setbacks, density, and permitted uses. Legal battles frequently ensue as developers and architects seek variances or rezoning approvals, facing opposition from local authorities and community groups concerned about overdevelopment or incompatibility with the neighborhood character. Architecture law defines the legal framework governing land use and the processes for obtaining necessary permits and approvals. Heritage preservation laws: when a proposed starchitect building is located within or adjacent to a historic district or involves the demolition of existing heritage structures, it can trigger intense legal scrutiny under heritage preservation laws. These laws aim to protect buildings and areas of historical, architectural, or cultural significance. Legal challenges often arise concerning the interpretation of heritage value, the impact of the new design on the historic context, and the adequacy of environmental impact assessments. Architecture law intersects directly with heritage law in these situations, requiring architects to navigate complex regulations and stakeholder interests. Public consultation and environmental impact assessment: many jurisdictions require public consultation and environmental impact assessments for significant development projects. Lawsuits can be filed challenging the adequacy of these processes, arguing that community concerns were not properly considered or that the environmental impact was not sufficiently evaluated. Architecture law includes the legal requirements for these participatory processes and the standards for environmental review. Aesthetic regulations and design review: some cities have aesthetic regulations or design review boards that evaluate the visual impact of proposed buildings. While often subjective, these regulations can become the basis for legal challenges if a design is deemed to be out of character with the surrounding environment or to negatively impact public views. Architecture law touches upon the legal enforceability of such aesthetic considerations. Liability and professional responsibility: architects have a professional responsibility to design buildings that comply with all applicable laws and regulations. If a starchitect design faces legal challenges due to non-compliance with zoning or heritage laws, the architect's professional liability and reputation can be at stake. Architecture law outlines the standards of professional conduct and the potential legal consequences of failing to meet those standards. This ongoing tension between avant-garde architectural ambition and the need to respect and preserve existing urban and historical contexts provides a compelling, contemporary case study in architecture law. It highlights the dynamic interplay between design innovation, regulatory frameworks, community interests, and the legal mechanisms used to mediate these often conflicting priorities. The outcomes of these legal battles shape the future of our cities and the evolving interpretation of architectural responsibility within a legal context. To elevate the concluding design project into a more advanced and technically rigorous exercise, the course could culminate in a small-scale architectural design and documentation endeavor, such as the schematic design and preliminary structural analysis of a conceptual, environmentally responsive micro-housing unit or a parametrically generated community hub. This final project would necessitate a sophisticated synthesis of design fundamentals, advanced visual communication techniques including parametric modeling and environmental performance simulations, a nuanced understanding of contextual influences encompassing site-specific microclimatic analysis and regulatory constraints, and a robust application of mathematical and structural principles involving preliminary load calculations, material selection based on structural efficiency and embodied energy, and geometric optimization for spatial organization and fabrication. Students would be required to produce a comprehensive set of deliverables, including detailed architectural drawings, site plans, floor plans, elevations, sections at varying scales, rendered visualizations demonstrating spatial qualities and material finishes, computational models illustrating the generative design process and environmental performance metrics e.g. solar gain, daylighting analysis, ventilation strategies, and a concise technical report outlining the design rationale. Material choices with justification based on structural and environmental considerations, and a preliminary structural concept demonstrating feasibility and adherence to relevant building codes and performance standards. This complex undertaking would serve as a demanding yet rewarding practical bridge to more advanced architectural studies, cultivating not only creative design thinking but also a foundational mastery of technical documentation, performance-driven design, and the integrated application of theoretical and mathematical frameworks within a tangible architectural proposition. Case study: a compelling case study that embodies the complexities of a technically advanced and environmentally responsive architectural design project, often encountering significant legal and regulatory hurdles, is the ongoing development and legal challenges surrounding the 580 Anton Boulevard project, formerly known American Samoa 1 Oak Brook Commons in Oak Brook, Illinois, USA. This ambitious project, initially envisioned as a high-rise residential tower designed with a strong emphasis on sustainability and innovative architectural forms, has faced years of legal battles and community opposition, primarily centered on zoning regulations, height restrictions, and environmental impact concerns. Here's how this case study aligns with the advanced design and technical considerations outlined. Environmentally responsive design: the project's design incorporates various sustainable features, potentially including high-performance facades, rainwater harvesting systems, passive solar design principles, and green roofs. The legal debates often involve scrutinizing the efficacy and long-term environmental impact of these features, requiring detailed technical documentation and potentially independent environmental assessments. This mirrors the course's emphasis on environmental performance simulations and material selection based on embodied energy. Parametrically generated forms and spatial optimization: contemporary high-rise designs often utilize parametric modeling to achieve complex geometries and optimize spatial organization for efficiency and aesthetics. The legal review process can involve detailed scrutiny of these computational models to ensure structural integrity, compliance with building codes especially regarding egress and fire safety in complex forms, and adherence to zoning envelopes. This reflects the course's inclusion of parametric modeling and geometric optimization. Site-specific microclimatic analysis and contextual influences: the design of a high-rise tower necessitates a thorough understanding of the site's microclimate, including wind patterns, solar exposure, and temperature variations. Legal challenges might arise if the environmental analysis is deemed insufficient or if the building's design is perceived to negatively impact the surrounding microclimate, e.g. creating wind tunnels or excessive shading. This aligns with the course's focus on site-specific microclimatic analysis. Preliminary structural analysis and material selection: the complex geometry and height of such a structure demand advanced structural engineering. Legal reviews often involve independent structural assessments to ensure the preliminary structural concept is sound and complies with stringent safety regulations, particularly in regions with seismic activity or high wind loads. Material selection based on structural efficiency, embodied energy, and durability is also subject to scrutiny. This resonates with the course's requirement for preliminary load calculations and justified material choices. Regulatory constraints and community opposition. The primary legal hurdles for the 580 Anton Boulevard project have stemmed from local zoning ordinances, particularly height limitations, and concerns raised by the community regarding traffic impact, viewshed obstruction, and the overall density of the development. These legal battles necessitate a deep understanding of local planning regulations and the ability to present technical data and design justifications that address these concerns. This mirrors the course's emphasis on understanding regulatory constraints. The protracted legal challenges faced by the 580 Anton Boulevard project exemplify the complexities of bringing an advanced, technically sophisticated, and environmentally conscious architectural design to fruition. The case highlights the critical interplay between innovative design, rigorous technical analysis, thorough environmental assessment, stringent regulatory frameworks, and community engagement, all factors that the advanced design project within the course aims to address and prepare students for navigating in their future architectural careers. The ultimate outcome of this project and the legal precedents it sets will have lasting implications for high-density, environmentally focused urban development. Advanced architectural design and innovation, building on foundational principles. Following the introductory exploration of architecture's historical, theoretical, and technical foundations, the next phase of study delves into advanced architectural design, integrating cutting-edge technologies, sustainability, and global challenges. This progression emphasizes critical thinking, innovation, and the application of interdisciplinary knowledge to complex real-world scenarios. Advanced design theory and computational methods. Building on design fundamentals, students engage with contemporary architectural theories, such as deconstructivism, parametricism, and biophilic design. Computational tools like Grasshopper for algorithmic modeling and Rhino enable the exploration of non-Euclidean geometries and dynamic forms. Case studies like Zaha Hadid's Haydar Aliyev Center Baku or the Beijing Daxing Airport designed with parametric efficiency illustrate how digital tools translate abstract concepts into built environments. Students analyze how algorithms optimize structural performance, material use, and aesthetic expression, pushing beyond traditional design constraints. Sustainable architecture and resilience. Expanding on sustainability principles, this module addresses climate-responsive design, circular economy practices, and net-zero energy systems. Tools like Ladybug Tools and Energy Plus simulate environmental performance, enabling students to model passive heating cooling, daylight optimization, and carbon footprint reduction. Case studies include the Edge Amsterdam, a smart building achieving BREEAM Outstanding certification, and Bosco Vertical Milan, integrating vertical forests for urban biodiversity. Students explore life cycle assessments LCA and cradle-to-cradle material strategies, emphasizing resilience in the face of climate change. Urban design and global contexts. Architecture's role in urbanization is critiqued through megacity case studies like Songdo IBD South Korea and Masdar City UAE. Topics include transit-oriented development TOD, mixed-use zoning, and equitable public spaces. Students engage with GIS mapping and urban analytics to address sprawl, density, and social equity, examining projects like Medellin's Metrosable, which combines infrastructure with community upliftment. The module challenges students to design adaptive frameworks for informal settlements or post-disaster recovery, balancing technical rigor with cultural sensitivity. Digital fabrication and material innovation. Advanced manufacturing techniques, such as 3D printed structures e.g. Icon's Vulkan printer and robotic assembly, redefine material possibilities. Students experiment with bio-based materials, mycelium composites, carbon sequestering concrete and adaptive facades e.g. Albar Towers responsive shading. Workshops on CNC milling and augmented reality AR for construction oversight, bridge digital design and physical execution, emphasizing precision and waste reduction. Professional practice and ethics. This module navigates the legal, economic, and ethical dimensions of architecture. Topics include BIM collaboration using Revit for clash detection and project management, intellectual property in design, and global standards like the AIA Code of Ethics. Case studies like the Grenfell Tower fire dissect regulatory failures, while debates on starchitecture critique the balance between iconic design and social responsibility. Students draft professional contracts, conduct risk assessments, and simulate public consultations to address NIMBYism and heritage conflicts. Final synthesis, Integrated Design Studio. The capstone project challenges students to design a mixed-use urban hub addressing climate resilience, community needs, and technological integration. Requirements include parametric modeling for site-specific solar wind analysis, BIM documentation with detailed MEP mechanical, electrical, plumbing systems, structural simulations using FEA software to validate seismic wind resistance, material passports tracking embodied carbon and recyclability, virtual reality VR walkthroughs for stakeholder engagement. Deliverables, a portfolio of renderings, technical drawings, simulation reports, and a public presentation defending design choices against ethical, environmental, and economic metrics. Emerging Frontiers. The course concludes with speculative topics, AI-driven generative design e.g. SpaceMaker AI, blockchain for smart contracts, and architecture's role in space colonization e.g. Mars habitats. Students critique the societal implications of these technologies, fostering a mindset of lifelong innovation and ethical stewardship. This advanced curriculum equips students to navigate architecture's evolving landscape, blending creativity with technical mastery to shape equitable, sustainable futures. Here are case studies that align with the modules outlined in the Advanced Architectural Design Curriculum, Advanced Design Theory and Computational Methods, The Kunsthausgras Austria by Peter Cook and Colin Fernier Cook Robotom Architectural Bureau, This amorphous, biomorphic building, often nicknamed the friendly alien, exemplifies the application of non-Euclidean geometries and challenged traditional architectural forms. Point 1 Its design process, while predating widespread parametricism, embodies a similar spirit of pushing beyond orthogonal constraints and exploring fluid, dynamic shapes. Analyzing its form generation, material choices, and structural solutions can provide insights into the translation of abstract concepts into built reality, even without relying solely on contemporary parametric tools. The Maxi National Museum of 21st Century Arts Rome by Zaha Hadid Architects. While the Haydar Aliyev Center is mentioned, the Maxi Museum offers another compelling case study of Hadid's exploration of dynamic forms and complex spatial relationships. Point 2 Its fluid lines, overlapping volumes, and interwoven circulation pathways demonstrate how digital tools enable the creation of intricate and spatially engaging environments. Studying its structural system and the translation of its complex geometry into buildable components offers valuable technical insights. Sustainable Architecture and Resilience, The Crystal London, UK by Wilkinson Eyre. This Sustainable Cities Initiative Centre showcases a holistic approach to environmental design. Its features include rainwater harvesting, blackwater treatment, intelligent building management systems, and extensive use of daylighting. Analyzing its energy performance data, material selection emphasizing recyclability, and its role as an educational hub for sustainable urban development provides a real-world example of BREEAM Excellence certification and integrated sustainability strategies. Point 3. Cheonggyecheon Stream Restoration Project, Seoul, South Korea. While not a building, this urban regeneration project demonstrates resilience and ecological restoration within a dense urban context. The daylighting of a previously covered stream, the creation of public green spaces, and the improvement of biodiversity illustrate how ecological principles can be integrated into urban design to enhance environmental quality and community well-being. This case study extends beyond building-scale sustainability to address broader urban resilience. Urban design and global contexts, superblocks in Barcelona, Spain. This urban planning initiative reclaims streets from vehicular traffic, creating pedestrian-prioritized zones with green spaces and community areas. Point 4. Studying the implementation, social impact, and economic effects of this strategy provides a compelling example of transit-oriented development and prioritizing equitable public spaces within a dense European city. It offers a contrasting perspective to the megacity examples and focuses on a more human-scale urban intervention. Elemental Social Housing Projects, Chile, by Alejandro Aravena. This architectural practice focuses on participatory design and incremental housing solutions for low-income communities. Their half-house concept, where residents are provided with a basic structural framework they can then expand and customize, offers a powerful case study in addressing social equity and providing adaptive frameworks for informal settlements. 5. It highlights a culturally sensitive and community-driven approach to urban development in a challenging context. Digital fabrication and material innovation. The Electrofilament Pavilion, V&A Museum, London, by H.M. Menges and ICDITKE University of Stuttgart. 6. This lightweight pavilion, robotically fabricated from woven carbon fiber, showcases the potential of advanced manufacturing techniques and material innovation in creating complex and structurally efficient forms. Analyzing its design process, material properties, and robotic assembly methods provides a tangible example of pushing the boundaries of traditional construction. The Tejuri Pavilion, Dubai, UAE, by Mean Middle East Architecture Network. This pavilion, 3D printed from locally sourced sand, demonstrates the potential of utilizing indigenous materials and additive manufacturing to create sustainable and contextually relevant architectural solutions. Studying its material composition, printing process, and its response to the desert climate offers insights into material innovation and reducing reliance on conventional, high-embodied energy materials. Professional practice and ethics. The Walkie Talkie Building, 20 Fenchurch Street, London, by Raphael Vinoli Architects. This controversial building, nicknamed for its distinctive shape, generated significant public criticism due to its glare reflecting onto nearby streets, melting parts of a car. 7. This case study provides a real-world example of the ethical considerations surrounding the impact of architectural design on the public realm and the potential for unintended negative consequences. Prompting discussions on architects' responsibility beyond aesthetics and functionality. The sinking of the Millennium Tower, San Francisco, USA. This luxury high-rise has been plagued by sinking and tilting issues since its completion. Analyzing the alleged design flaws, foundation problems, and the ensuing legal battles between the developers, architects, and residents offers a complex case study in professional liability, structural integrity, and the long-term consequences of design and construction errors. It underscores the critical importance of thorough engineering and adherence to building codes. These case studies offer diverse examples that align with the advanced topics in the curriculum, providing students with real-world precedents to analyze, critique, and learn from as they develop their own integrated design projects. Architecture is a science arising out of many other sciences, and adorned with much and varied learning, by the help of which a judgment is formed of those works which are the result of other arts. Marcus Vitruvius Pollio. Conclusion, reflecting on the foundations and future of architectural practice. As we conclude this introductory architecture course from the J.O.L.A.L.F, we stand at the intersection of history, creativity, science, and societal responsibility, having explored the multifaceted discipline that is architecture. This course has served as a foundational journey, illuminating the principles, processes, and profound impacts of architectural design. From the rudimentary shelters of J.O.L.A.L.F to the parametric sophistication of modern marvels like the J.O.L.A.L.F Center, we have traced the evolution of architecture as both a practical necessity and an artistic endeavor. Through this exploration, we have come to understand architecture not merely as the construction of buildings but as a dynamic synthesis of form, function, context, and innovation that shapes the human experience and responds to the challenges of its time. The course has introduced us to the core tenets of architectural design: form, function, space, and order, underscored by the elemental vocabulary of line, shape, volume, light, color, and texture. Case studies like the Bauhaus Dessau and the Salk Institute have demonstrated how these principles are orchestrated to create spaces that are both functional and profoundly meaningful. We have delved into the critical role of visual communication, mastering the language of plans, elevations, and sections, as exemplified by the meticulous documentation of the Sydney Opera House. These tools are not just technical necessities but the bridge between imagination and reality, enabling architects to translate abstract ideas into tangible environments. Mathematics has emerged as an indispensable ally in this process, from the Euclidean geometry that defines spatial relationships to the trigonometry ensuring structural stability in geodesic domes and the advanced computational methods powering parametric designs like the Millau Viaduct. These mathematical underpinnings remind us that architecture is as much a science as it is an art, requiring precision and rigor to achieve both safety and aesthetic harmony. The integration of advanced tools like AutoCAD architecture and computational fluid dynamics (CFD) has further highlighted how technology amplifies the architect's ability to innovate and optimize, as seen in projects like the Gherkin and the Bullitt Center. Context and environment have been central to our discussions, emphasizing that architecture is inseparable from its social, cultural, and ecological surroundings. The Siheyuan courtyard houses of Beijing and the sustainable design of the Bullitt Center illustrate how architecture responds to the needs, values, and climates of its place. Sustainability, in particular, has emerged as a non-negotiable imperative, urging us to design with the future in mind, minimizing ecological impact, maximizing resilience, and fostering human well-being. The Earthship Biotecture case study powerfully encapsulates this ethos, blending mathematical precision, recycled materials, and a radical vision of self-sufficiency to redefine what architecture can achieve. We have also grappled with the distinction between architecture and building, a theme eloquently articulated by Dana Arnold and echoed in Thomas Jefferson's call to elevate architecture into an art form that chews so much. The Barcelona Pavilion and the Crystal Palace demonstrate how thoughtful design transcends mere utility, creating spaces that inspire, provoke, and endure. Yet, we have also confronted the sobering realities of architectural failure, as seen in the tragic collapse of the Rana Plaza, underscoring the critical importance of robust building codes, ethical practice, and rigorous oversight. The historical arc of architecture, from the megalithic precision of Stonehenge to the Roman engineering feats of the Pantheon, and from the spiritual grandeur of Notre Dame to the raw expressiveness of brutalist icons like the Unite D habitation, has revealed a discipline in constant dialogue with its cultural and technological context. Each era has left its mark, building on the achievements of its predecessors while pushing the boundaries of what is possible. This historical perspective grounds us in the understanding that architecture is a living tradition, continually evolving to meet new challenges, whether they be urbanization, climate change, or technological disruption. Looking forward, the advanced modules outlined in the curriculum parametric design, sustainable resilience, urban planning, digital fabrication, and professional ethics beckon us toward a future where architecture plays a pivotal role in addressing global crises. Projects like Bosco Vertical and the Superblocks of Barcelona point to a world where architecture fosters biodiversity, equity, and community. Technologies like Grasshopper, BIM, and 3D printing, as seen in the Electrofilament Pavilion, promise unprecedented creative and constructive possibilities. Yet, cases like the Grenfell Tower fire and the legal battles over Starchitect designs remind us that innovation must be tempered with responsibility, humility, and a commitment to the public good. This course has not only equipped us with foundational knowledge and skills but also ignited a curiosity and passion for architecture's potential to shape a better world. As Marcus Vitruvius Pollio reminds us, architecture is a science enriched by many disciplines, requiring both technical mastery and creative vision. The final design project, a conceptual microhousing unit or community hub, has challenged us to synthesize these lessons, integrating design fundamentals, mathematical rigor, environmental responsiveness, and contextual sensitivity into a cohesive proposition. This exercise mirrors the real-world complexities faced in projects like the 580 Anton Boulevard, where innovation, regulation, and community engagement must converge. In closing, architecture is a calling that demands both heart and mind, creativity and discipline, individuality and collaboration. As we move forward, let us carry Jefferson's aspiration to infuse taste into this vital art, ensuring that our designs not only meet the needs of today but also inspire and sustain future generations. Whether designing a humble dwelling or a transformative urban hub, we are tasked with creating spaces that resonate with meaning, foster connection, and stand as testaments to human ingenuity. This course is but the beginning, a foundation upon which to build a lifelong journey of learning, questioning, and creating in the ever-evolving field of architecture. Appendix: Expanding on the foundations and future of architectural practice. This appendix provides supplementary material to enrich the understanding of the Introductory Architecture course from the J.O.L.A.L.F, offering additional context, technical details, and resources to deepen the exploration of architectural principles, historical case studies, and emerging trends. It is structured to align with the key themes of the course: conclusion, design fundamentals, visual communication, mathematics, context and environment, sustainability, historical evolution, and advanced architectural practice, while introducing further case studies, tools, and theoretical perspectives to support continued learning and application. Expanded case studies. To complement the case studies in the conclusion, the following examples provide additional insights into how architectural principles are applied across diverse contexts, scales, and challenges. Design fundamentals, Tadao Ando's Church of the Light, Osaka, Japan. Relevance: this minimalist concrete structure exemplifies the interplay of form, space, and light as fundamental design elements. Details: completed in 1989, the Church of the Light uses simple geometric forms, a rectangular box with a cross-shaped cutout in the wall, to create a profound spatial experience. The precise manipulation of natural light transforms the interior, highlighting the texture of raw concrete and evoking a sense of spirituality. Analysis: Ando's design demonstrates how limited materials and a restrained palette can achieve emotional depth, reinforcing the course's emphasis on the power of basic elements: line, shape, volume, light. The negative space created by the cross becomes as significant as the positive form of the building itself. Learning application: students can analyze how endo balances form and function to create an introspective environment, sketching sections to explore light penetration and spatial flow. Visual communication, Centre Pompidou, Paris, France. Relevance, designed by Renzo Piano and Richard Rogers 1977, this iconic building showcases the importance of clear visual communication in translating radical design concepts. Details, the Centre Pompidou's inside-out design, with exposed structural and mechanical systems, required meticulous architectural drawings to coordinate its complex engineering. Plans, sections, and exploded axonometric drawings were critical in communicating the placement of colorful ducts, steel trusses, and modular components. Analysis, the project highlights the role of standardized drafting conventions, e.g. line weights, annotations, in ensuring clarity across multidisciplinary teams. Its bold aesthetic also sparked debates about architecture versus engineering, aligning with the course's distinction between architecture and building. Learning application, students can practice creating annotated elevations and sections of a similarly complex structure, focusing on clarity and precision in representing structural and mechanical elements. Mathematics in architecture, the Eden Project, Cornwall, UK. Relevance, designed by Nicholas Grimshaw 2001, the Eden Project's biomes illustrate the application of advanced geometry and structural analysis. Details, the biomes are composed of hexagonal and pentagonal geodesic frameworks, inspired by Buckminster Fuller's principles, clad in ETFE ethylene tetrafluoroethylene cushions. Finite element analysis via and parametric modeling were used to optimize the lightweight steel frames for structural efficiency and environmental performance. Analysis, the project demonstrates how geometry, hexagonal tessellation, and trigonometry calculating angles for frame connections enable large-span, sustainable structures. It also showcases computational tools in achieving organic forms that mimic natural systems. Learning application, students can experiment with basic parametric modeling, e.g. using Grasshopper to generate a simplified geodesic structure, calculating surface areas and material quantities. Context and environment, the Great Mosque of J.O.L.A.L.F. Relevance, this UNESCO World Heritage Site exemplifies architecture deeply rooted in its cultural and environmental context. Details, rebuilt in 1907 on earlier foundations, the mosque is constructed from sun-baked mud bricks, adobe, and coated with plaster, a material choice driven by the arid Sahel climate. Its organic forms and annual community-led maintenance reflect local traditions and social cohesion. Analysis, the mosque's design responds to environmental constraints, heat, scarce resources, and cultural values, communal identity, Islamic aesthetics, aligning with the course's focus on context-driven design. Its impermanence contrasts with Western notions of monumental architecture, prompting reflection on durability versus adaptability. Learning application, students can research vernacular architectures in their own regions, analyzing how materials and forms respond to local climates and cultural practices. Sustainability, 1 Angel Square, Manchester, UK. Relevance, designed by 3D Reed 2012, this office building for the cooperative group is a model of sustainable design in a commercial context. Details, achieving a BREEAM Outstanding rating, the building features a double skin facade for thermal regulation, a combined heat and power CHP system fueled by biofuel, and extensive daylighting. Computational simulations, e.g. CFD for airflow, Energy Plus for energy modeling optimized its performance. Analysis, the project integrates passive and active sustainability strategies, demonstrating how mathematical modeling and material innovation reduce environmental impact while maintaining functionality. It also reflects corporate social responsibility, aligning with the course's emphasis on social influences. Learning application, students can conduct a simplified daylight analysis for a small building using free tools like Diva for Rhino, exploring how window placement affects energy efficiency. Historical evolution, the Hagia Sophia, Istanbul, Turkey. Relevance, constructed in 537 CE under Emperor Justinian I, the Hagia Sophia represents a pinnacle of Byzantine architecture and engineering. Details, its massive central dome, supported by pendentives and semi-domes, was a groundbreaking feat, achieved through empirical knowledge and early structural calculations. The interplay of light through clerestory windows and mosaics creates a transcendent interior. Analysis, the Hagia Sophia bridges ancient and medieval architectural traditions, illustrating how engineering innovation, e.g. pendentive dome construction, serves spiritual and political purposes. Its multiple transformations, church, mosque, museum, mosque, again highlight architecture's adaptability to shifting cultural contexts. Learning application, students can sketch the structural system of the dome, analyzing how forces are distributed, and compare it to modern dome designs like the Eden Project. B. Technical tools and resources. To support the technical skills introduced in the course, the following tools and resources are recommended for students to explore further, enhancing their ability to design, analyze, and communicate architectural ideas. AutoCAD Architecture. Purpose: streamlines drafting with intelligent objects for walls, doors, and windows. Resource: Autodesk's free educational license available at autodesk.com. Education provides access to AutoCAD architecture, including tutorials on creating parametric objects and generating schedules. Application: practice creating a small residential floor plan, using dynamic blocks to adjust window sizes and auto-generating a door schedule. Rhino and Grasshopper. Purpose: Rhino supports 3D modeling, while Grasshopper enables parametric design for complex geometries. Resource: Food for Rhino. Foodforrhino.com offers free Grasshopper plugins like Ladybug for environmental analysis. The Think Parametric YouTube channel provides beginner-friendly tutorials. Application: model a simple parametric facade, adjusting parameters to optimize solar shading based on site-specific sun angles. Revit for BIM. Purpose: facilitates building information modeling for coordinated design and documentation. Resource: Autodesk's Revit tutorials. Knowledge.autodesk.com cover creating families, clash detection, and rendering. Lynda.com via LinkedIn Learning offers project-based courses. Application: develop a BIM model of a micro-housing unit, including MEP systems, and export a material takeoff to estimate costs. Environmental analysis tools. Purpose: simulate energy performance, daylighting, and thermal comfort. Resource: Ladybug Tools. Ladybug.tools integrates with Grasshopper for free solar, wind, and daylight analysis. Cifira.com offers cloud-based energy modeling trial available. Application: analyze a classroom design for daylight factor and annual energy consumption, proposing glazing adjustments to improve performance. Structural analysis software. Purpose: perform preliminary structural calculations for load-bearing elements. Resource: free tools like SkySieve. Structural 3D. SkySieve.com allows students to model beams and frames, calculating shear and moment diagrams. Oasis GSA. Oasis-software.com offers educational licenses for FIA. Application: model a simple steel frame for a pavilion, analyzing deflection under wind loads and optimizing member sizes. See theoretical perspectives. To deepen the intellectual engagement with architecture, The following perspectives expand on the course's theoretical underpinnings, encouraging critical thinking about architecture's role in society. Vitruvius's triad: strength, utility, beauty. Concept: Marcus Vitruvius Polio's principles from the architecture of 1st century BCE remain a cornerstone of architectural theory, balancing structural integrity, functional efficiency, and aesthetic appeal. Application: evaluate a contemporary building, e.g. One Angel Square against these criteria, considering how modern sustainability goals reinterpret beauty as environmental harmony. Resource: Vitruvius's 10 books on architecture. Dover Publications is accessible for students to explore primary texts. Phenomenology in architecture. Concept: philosophers like Martin Heidegger and architects like Giovanni Pallasmaa emphasize architecture's experiential qualities, focusing on how spaces evoke emotions and sensory responses. Application: analyze the Church of the Light or the Salk Institute for their phenomenological impact, noting how light and materiality shape user perception. Resource: Pallasmaa's The Eyes of the Skin. Wiley offers an accessible introduction to sensory-driven design. Critical regionalism. Concept: advocated by Kenneth Frampton, critical regionalism seeks a balance between global architectural trends and local traditions, resisting homogenized modernism. Application: compare the Great Mosque of Jin with a modern regionalist project like Guangzhou's Ningbo History Museum, assessing how both integrate local materials and cultural identity. Resource: Frampton's Essay Towards a Critical Regionalism in the Anti-Aesthetic, ed. Hal Foster provides a concise theoretical framework. Postmodernism and deconstructivism. Concept: postmodern architects like Robert Venturi and deconstructivists like Frank Gehry challenge modernist orthodoxy, embracing complexity, irony, and fragmented forms. Application: study the Guggenheim Bilbao for its deconstructivist geometry, contrasting it with the modernist simplicity of the Bauhaus Dessau. Resource: Venturi's Learning from Las Vegas MIT Press and Charles Jenks's The Language of Postmodern Architecture. Rizzoli offer foundational texts. De-emerging trends and speculative futures. Building on the advanced curriculum, the following trends and speculative ideas provide a glimpse into architecture's future, encouraging students to think beyond current practices. AI-driven generative design. Overview: tools like SpaceMaker AI and Autodesk's Project Refinery use machine learning to generate thousands of design options based on parameters like site constraints, zoning, and sustainability goals. Case study: the Autodesk Technology Center Boston used generative design to optimize floor plans for daylight and circulation, reducing energy use by 10%. Implication: AI could democratize design but raises ethical questions about authorship and cultural sensitivity. Resource: explore Autodesk's generative design tutorials. Autodesk.com Solutions Generative Design. Circular architecture. Overview: the circular economy emphasizes designing for disassembly and material reuse, minimizing waste. Case study: the Triadoesbank Netherlands by Rauw Architects is designed for full disassembly, with a material passport tracking all components. Implication: circular principles challenge traditional construction, requiring new skills in life cycle assessment and modular design. Resource: Ellen MacArthur Foundation's Circular Economy Resources. ellenmacarthurfoundation.org. Space architecture. Overview: designing habitats for Mars or lunar bases involves extreme environmental constraints, requiring lightweight, modular, and self-sustaining structures. Case study: Big S Mars Science City UAE simulates a Martian colony, integrating 3D printed regolith structures and hydroponic agriculture. Implication: Space architecture pushes interdisciplinary collaboration, blending architecture with aerospace engineering and biology. Resource: NASA's 3D printed habitat challenge. nasa.gov provides open access design briefs. Biomimetic design. Overview: inspired by natural systems, biomimicry uses principles like termite mound ventilation or lotus leaf water repellents to inform design. Case study: the Eastgate Center, Harare, Zimbabwe by Mick Pierce uses biomimetic ventilation inspired by termite mounds, reducing energy use by 90% compared to conventional buildings. Implication: biomimicry offers sustainable solutions but requires deep ecological knowledge. Resource: Biomimicry Institute's Ask Nature database. AskNature.org catalogs natural design strategies. Practical exercises and projects. To reinforce the course's learning objectives, the following exercises encourage hands-on application of concepts and tools. Sketching exercise: spatial analysis. Task: select a local public building, e.g. a library or community center. Sketch a section and plan, noting how light, volume, and circulation shape the user experience. Objective: develop observational skills and understand spatial relationships. Parametric modeling challenge. Task: using Grasshopper, design a modular facade panel that adjusts to solar angles. Export the model to Rhino for rendering. Objective: gain familiarity with parametric tools and environmental responsiveness. Sustainability simulation. Task: use Ladybug tools to analyze a hypothetical classroom's daylight and energy performance. Propose design changes to reduce energy use by 20%. Objective: apply computational analysis to optimize building performance. Historical comparative study. Task: compare the structural systems of the Hagia Sophia and the Eden Project, creating diagrams to illustrate load distribution. Write a 500-word essay on how each reflects its era's technological and cultural priorities. Objective: synthesize historical and technical knowledge. Urban design proposal. Task: design a small public plaza for a local site, incorporating transit-oriented design principles and sustainable materials. Produce a site plan, section, and rendered perspective. Objective: integrate contextual and environmental considerations into urban design. Recommended reading and media. To Inspire provides a curated list of resources to further students' exploration of architecture. Books. A Pattern Language by Christopher Alexander et al. Oxford University Press, a seminal text on design patterns for human-centered spaces. The Architecture of Happiness by Alain de Botton Vintage, explores the emotional impact of architecture. Cradle to Cradle by William McDonough and Michael Braungart, North Point Press, advocates for sustainable design principles. Documentaries and films. My Architect 2003, a personal exploration of Louis Kahn's life and work. The Human Scale 2012, examines urban design through J.O.L.A.L's human-centered approach. Building the Future, Sustainable Architecture BBC, showcases innovative green buildings. Online platforms. ArchDaily. ArchDaily.com, features contemporary projects and articles. Dezeen.com, covers architecture, design, and technology trends. The Architectural Review. Architectural-review.com, offers in-depth essays and critiques. Glossary of key terms. Parametric design, a process using algorithms to generate forms based on defined parameters. Finite element analysis (FEA), a computational method to analyze structural behavior under loads. Computational fluid dynamics (CFD), simulates fluid flow, heat transfer, and related phenomena. Building Information Modeling (BIM), a digital process for creating and managing building data. Life Cycle Assessment (LCA) evaluates a building's environmental impact from construction to demolition. This appendix serves as a bridge between the foundational knowledge gained in the introductory course and the advanced skills needed for future architectural practice. By engaging with these case studies, tools, theories, and exercises, students can continue to build their expertise, preparing to contribute meaningfully to the evolving field of architecture. As Thomas Jefferson envisioned, let us strive to infuse taste and responsibility into this vital art, creating spaces that endure, inspire, and sustain.
Brick by brick, I lay my name through the fire and through the flame, chasing dreams they call insane, but I'll rise up just the same. Hammer strikes and echoes loud, building towers through the clouds. No one's stopping me tonight. I've got the plans, I'll win this fight. Every man builds his own way, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain. My fate, facing trials I won't break. Every stumble fuels my flame. I'm the one who writes my name. The world's a canvas, raw and white. I hold the brush, I won't hide. Colors bold, they light my trail. I'll succeed, I will prevail. Every man builds his own way, into the day. Fortunes forged by sweat and pain. We are architects of the rain. Stone by stone I carve my fate, through the night into the day. Fortunes forged by sweat and pain. We are architects of the rain.